In mathematics, there are areas that focus purely on the study and discovery of the patterns that numbers create. Maybe you've heard of the Fibonacci sequence or the 3x plus 1 problem. While the problems we're going to see at this level of algebra are not quite the same as what these two problems create, they're still patterns nonetheless. The FOIL method that was introduced in the last lesson creates several patterns within itself, two of which is an introduction to an advanced concept we'll explore much later in college level algebra. Recall that we can use the FOIL method to multiply two binomials very quickly to produce a trinomial, such as x plus 3 times x minus 3. If we use the FOIL method on this, we get x squared minus 3x plus 3x minus 9, which becomes x squared minus 9. Well, this is different. All the binomials of one variable we had multiplied last lesson produced trinomials. Why did this one produce a binomial? Let's try another. X plus 5 times x minus 5. This becomes x squared minus 5x plus 5x minus 25, which simplifies to x squared minus 25. Again, we have a binomial. Can you see the pattern yet? Whenever you multiply two binomials that only differ in the sign of the second term, we end with a difference of squares. Let's use another example that we'll use as a definition. X plus y times x minus y. This is equal to x squared minus xy plus xy minus y squared, which simplifies to x squared minus y squared. If we use just the variables, we can clearly see that multiplying two binomials of differing signs produces a difference of squares. For the definition for the sum and difference of same terms, we have for all x and y in R, that is all x and y in all real numbers, x plus y times x minus y equals x squared minus y squared. This states that if we have a binomial product of the sum and difference, then we can simply write it out as the square of the first term minus the square of the second term. Notice that the answer will be a difference because our final operation, the positive y and the minus y, produces the minus y squared. Let's check out a few examples. Number 1, 2x plus 10 times 2x minus 10. Since the only difference here is the signs, we don't have to use the FOIL method, because the FOIL method tells us that the answer is going to be x squared minus y squared. But we see a coefficient with the x terms. All we had to do is treat the 2x as the whole x part of the formula. So the answer is 2x squared minus 10 squared, which equals 4x squared minus 100. Number 2, 3x plus 4y times 3x minus 4y. Here both terms have coefficients. We treat both variables with their coefficients as the x and y variables. Therefore, the answer is 3x squared minus 4y squared, which equals 9x squared minus 16y squared. What if the two binomials are the same? Does another pattern appear? Let's continue using the same constants. X plus 3 times x plus 3. First of all, notice that we can consider this as a product repetition of two terms. It can be thus written as an exponent, x plus 3 squared. Using FOIL, we get x squared plus 3x plus 3x plus 9, which simplifies to x squared plus 6x plus 9. Okay, we see that our answer, a trinomial, has coefficients that contain a factor of our original constant, 3. Let's see if the other does the same. X plus 5 times x plus 5. This equals x squared plus 5x plus 5x plus 25, which simplifies to x squared plus 10x plus 25. Once again, we have a trinomial that contains coefficients that contain a factor of our original constant. I think we have a pattern. Let's use only variables in one more example to see if we can write out a definition. X plus y times x plus y. This equals x squared plus xy plus xy plus y squared. This simplifies to x squared plus 2xy plus y squared. This leads us to a definition, the square of a binomial. For all x and y in or, that is all real numbers, we have x plus y squared equals x plus y times x plus y, which equals x squared plus 2xy plus y squared. When we have a binomial that is squared, or a repeated product of a binomial, we can write it out as the square of the first term plus twice the product of the first and second term plus the square of the second term. Here's a few examples to show it in action. Number 1, 5x plus y squared. Remember that we think of the whole term as a variable part in the formula. So we have 5x squared plus twice the first term times the second term plus the square of the second term. So we have 25x squared plus 10xy plus y squared. Number 2, 6x plus 7y squared. By now, we should be used to using whole terms as a variable part in formulas. We have 6x squared plus twice of 6x times 7y plus 7y squared. This becomes 36x squared plus 84xy plus 49y squared. This might look a bit strange as an answer, but remember that the x terms have a common factor, 6, and the y terms have a common factor, 7. Notice in number 1 that the answer, 25x squared, that's supposed to be a plus 10xy plus y squared, has 5 as a common factor for the first two terms, because the 5 was part of the original binomial. Number 3, 2x plus 3y squared. I want to illustrate the point I made in the last example by using smaller numbers. I'm also purposely using even and odd numbers for the coefficients because it'll be easier to see the pattern. We have 2x squared plus 2 times 2x times 3y plus 3y squared. This equals 4x squared plus 12xy plus 9y squared. The x variables have a 2 as the common prime factor, and the y variables have a 3 as a common prime factor. Finally, notice that the middle x and y term contains a common factor for both the x and y terms. We'll eventually cover a subject called the binomial theorem towards the end of algebra that will help in understanding this idea. In fact, the binomial theorem will show up many times after that in many different definitions and theorems. Number 4, 2x minus 3y squared. I want to illustrate what happens if we square a binomial difference. So we have 2x squared plus 2 times 2x times negative 3y. Never forget your signs. Plus negative 3y squared. This becomes 4x squared minus 12xy plus 9y squared. Notice that our answer is almost the exact same as number 3, for the exception of the sign of the second term. Since the second term is being squared for our third term in our answer, it's going to be positive. That's why you will only have a negative in the second term. So if you wanted to write a definition for x minus y squared, you would have x squared minus 2xy plus y squared. What you might see in many textbooks is you'll see a strange symbol called plus or minus. So it's quite possible you may see as x plus or minus y squared equals x squared plus or minus 2xy plus y squared. So whenever this sign is a plus, this sign is a plus, and whenever this sign is a negative or minus, this sign is a minus. Let's produce one more pattern that appears quite frequently, but is a little bit more difficult. We showed that we can multiply a squared binomial, such as x plus 3 squared. But what if it was cubed, such as x plus 3 cubed? Bear in mind that cubes tend to cause numbers to grow quite rapidly. So for now, I'll try to use smaller numbers until we're used to using larger number cubes. We know that x plus 3 cubed is equal to x plus 3 times x plus 3 times x plus 3. FOIL taught us how to multiply two binomials, not three. So let's just use FOIL on the first two binomials. This leads us to x squared plus 6x plus 9 times x plus 3. Even though FOIL won't get us any further, we can continue multiplying using the old method by holding one of the polynomials as a single term. Let's hold x plus 3 as the variable a, and this will give us, using distribution, ax squared plus a6x plus a9, which we write as x plus 3 times x squared plus x plus 3 times 6x plus x plus 3 times 9. Using distribution, we have x cubed plus 3x squared plus 6x squared plus 18x plus 9x plus 27. And then simplifying our like terms, we have x cubed plus 9x squared plus 27x plus 27. Notice, just as with the square of a binomial, we have an answer with coefficient factors of 3, our original constant. So there was definitely a pattern here too. Let's go ahead and use only variables to produce a definition. X plus y cubed, which we know is x plus y times x plus y times x plus y. Using FOIL, we get x squared plus 2xy plus y squared times x plus y. Holding x plus y to equal a, we get ax squared plus a2xy plus ay squared, which is equal to x plus y x squared plus x plus y times 2xy plus x plus y times y squared. Distributing across, we get x cubed plus x squared y plus 2x squared y plus 2xy squared plus xy squared plus y cubed. And finally, we can combine like terms, which gives us x cubed plus 3x squared y plus 3xy squared plus y cubed. Definition of a cube of a binomial. For all x and y in R, we have x plus y cubed is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. This states that the cube of a binomial is equal to the cube of the first term plus 3 times the product of the square of the first term and the second term plus 3 times the product of the first term and the square of the second term and plus the cube of the second term. This final formula seemed like quite a bit. We'll work a few examples to help cement it in our minds. Number 1, 2x plus y cubed. Let's use the formula for the cube of a binomial and plug in the correct terms. So we have 2x cubed plus 3 times 2x squared times y plus 3 times 2x plus y squared plus y cubed. This equals 8x cubed, 12x squared y plus 6xy squared plus y cubed. We also see that the x terms have the common prime factor of 2. Number 2, 2x plus 3y cubed. Using the formula, we have 2x cubed plus 3 times 2x squared times 3y plus 3 times 2x times 3y squared plus 3y cubed. This is equal to 8x cubed plus 36x squared y plus 54xy squared plus 27y cubed. Notice that the x terms have 2 as a prime factor and the y terms have 3 as a prime factor. Number 3. Now we have a negative for a second term. Let's fill in our parts for the formula. 3x cubed plus 3 times 3x squared times negative 4y plus 3 times 3x times negative 4y squared plus negative 4y cubed. Now these numbers are going to be a little bit bigger. So we have 27x cubed minus 108x squared y plus 144xy squared minus 64y cubed. Using the FOIL method, we have found 3 formulas that we can use to make our work much more efficient. These types of tricks can be used all over math. For example, I've used the same type of trick in calculus. In the next lessons, we'll start to take a deeper look at the multiplication of polynomials. But first, we have to cover a very foundational concept, the greatest common factor.